Today we're going to be talking about some new ways to calculate delta H values for chemical reactions. In previous videos we discussed using Hess's law to do this. Today we'll be discussing how information from bond enthalpies and heats of formation can get us to the same exact answer. A quick rundown of the learning objectives of this video. We're going to again review the different ways we can get delta H values from either measurement or calculation. You've seen this before, but I want to make sure that we're clear on the different ways of doing it so you start grouping these ideas together. We're then going to focus on the two new techniques for calculating delta H, the first of which being bond enthalpies, the energy associated with individual chemical bonds. We'll define the term and then talk about how this data can be used to calculate these delta H values. Secondly, we'll talk about heats of formation. Heats of formation involves not bonds, but entire chemical compounds and the energy associated with those. We'll define that term again and then talk about how heats of formation data can be used to calculate the delta H of a reaction. Over on the right, we'll talk about the two graphs we have here in a little more detail later, but all of these types of calculations are very data-driven, meaning you're going to have tables containing lots of information, and from that information you're going to combine it in a certain way using formulas to calculate our ultimate delta H. Both of these tables are available in links down below on the bottom of the page, and I encourage you either now or during the video to download these, get these printed out so that you have them for class time and also have them for the examples we're about to do. Just again to go over a quick recap of the different ways we can get delta H values. The first way we talked about, which was a lab you guys worked on, was how to measure delta H values through a process known as calorimetry. And if you recall, that involved a setup similar to the one we have over here on the side of the screen. You have an insulated cup with a reaction running on the inside. That reaction causes water temperature to change, which is read by the thermometer, which again can be correlated back to a delta T, which eventually ties back to a delta H. All enthalpy data at some point has to come from a calorimeter, but once you have enough of this calorimetry data gathered, you can start using other data from other reactions to calculate the delta H of your particular reaction. It'll save you some lab time. We've already gone through this list, so I'm not going to go through it in too much detail again. Last time we talked about Hess's law as a tool to calculate delta H. Today we're going to focus on the other two here. We're going to focus on how bond enthalpies and heats of formation can be used to calculate delta H values. The first new tool we're going to explore for calculating delta H then is going to be bond enthalpies, and I'd like to start with a quick definition of what a bond enthalpy really is. Basically, it's the energy needed to break apart a chemical bond. If you recall from earlier in the year, we talked about how chemical bonds have a certain amount of stored energy inside them. Basically, when you're dealing with bond enthalpies, it's a kind of a measurement of that energy and or a measurement of the energy needed to break that bond. This energy, unfortunately, though, is not constant, depending on the environment that your bond is in. If it's dissolved in water, if it's a gas floating around with other gases, what other chemicals around, etc., that's going to affect the energy associated with this bond. It's going to affect how much energy it needs to break it. Some bonds break easier in different conditions than others. As a result of that, when you're looking at bond enthalpy data, it's not going to be the actual bond enthalpy you're looking at. Instead, you're going to be looking at data that talks about an average bond enthalpy. It's basically all the different types of bond enthalpies that could possibly exist in possible different conditions, averaged together to make a value that represents all of them. Now, we talked about this again earlier in this chapter. When you break these bonds, you get this idea of energy being released, and the reason it's being released is because you're getting the potential energy stored in the bond being released in the form of kinetic energy, and if we recall, kinetic energy is what we typically associate with heat, and that's the stuff we can measure using our calorimeter. Since heat is coming out, we would describe this process as being exothermic. And likewise, we can talk about bonds being formed. When we make new chemical bonds, we're taking that kinetic energy, that heat energy, and converting it back into the stored potential energy in the bond. This process we would describe as being endothermic. The bonds themselves are absorbing heat energy. Because heat's being absorbed, we would expect this surrounding solution to feel cooler. And again, the other idea of heat being drawn in. We can then keep track, if you want to look at all this together, we can keep track of the number of bonds broken and the number of bonds formed, and any difference, a deficit or an excess between those two things, will ultimately be the net energy in or the net energy out of your process, which we can then correlate back to a value of delta H for the entire reaction. So again, what we're going to be looking at in the future is we can take all the bonds broken and how much energy was released, all the bonds formed and how much energy was absorbed. And the end result is we can calculate a delta H from that by seeing how different that they are. This mathematics can then be summarized into an equation that we can use. And again, the goal is going to be to calculate the delta H of our chemical reaction. So that's going to be the result of this math here. And what we see here is some terminology, some mathematical terminology you may not be familiar with. This little symbol here is the Greek letter sigma. It's capital sigma. And it basically means the sum, in case you haven't come across this in your math classes yet. So what we want to do in this calculation is take the sum of all the energy from the bonds broken and subtract out the sum of all the energy from the bonds formed. And the difference between those two values is going to get us the net amount of energy that's either left over or the net amount of energy we'll need. That again will correlate back to our value for delta H. Now, to do this process, we got a couple things we have to worry about. First of all, you have to be able to identify which bonds are broken and which bonds are formed. For example, carbon to hydrogen bonds or carbon to oxygen bonds. You got to see what those are first. In order to do this, you need to know about something known as a Lewis dot structure. This is something we'll tackle a little bit later on in the year. In fact, I believe it's our next chapter. But a Lewis dot structure is basically a model representing the atoms involved in your chemical and how they're connected together. For example, the formula of this compound that just popped up on the screen here is CH2O. I don't think it's necessarily obvious at this stage in the game to recognize that the carbon has two hydrogens attached to it. So that's two carbon to hydrogen bonds and one carbon to oxygen double bond. I think this one in particular is hard to spot. We would need to see that in advance before we can figure out which bonds are broken and which bonds are formed. For now, the way we're going to solve this problem is I will always provide you with this picture here, this Lewis dot structure. Later on in the year when you can do your own, you'll have to go from the formula, create the Lewis dot structure first, and then calculate your bond enthalpies from that. Once you know the actual bonds that are broken and formed, the data, the actual enthalpies, can be looked up on a data table that will be provided for you. This data table is attached to the bottom of the web page that this video is on. I recommend pausing the video right now, downloading this data table, and quite frankly, the other one that's down there, printing these things out or saving them so that you have them at your disposal later on. These are the numbers we're going to use to actually solve problems, so if you don't have the data table, you're going to have a lot of trouble. Finally, once you've identified bonds broken and formed, once you've looked up all your data values, it's simply a matter of plugging them into the equation above and calculating the actual delta H for the overall process. And that's exactly what we're going to do next. I'm going to show you reaction on the next slide, and then we'll calculate the delta H of it using bond enthalpy data. So here's our chemical reaction. We have the chemical propane being combusted. It's reacting with oxygen to make carbon dioxide and water. Our interest here is calculating the delta H of reaction using bond enthalpy data. Now, as I said, we cannot calculate it using this form of the equation yet because we don't know what bonds are present, although in some cases you can make guesses. What we do need to see is more information like this, the Lewis dot structures for each of these compounds that allows us to see that C3H8 is really made up of 1, 2, 3, 4, 5, 6, 7, 8 carbon to hydrogen bonds. 8 carbon to hydrogen bonds. That O is actually double bonded together to give us 5 oxygen to oxygen double bonds. We then create on this side a bunch of carbon-oxygen double bonds in our CO2, which means we're going to get 6 carbon to oxygen double bonds. And then finally here, we get oxygen to hydrogen bonds in water. We're going to get 8 oxygen to hydrogen bonds here. Again, 2 bonds for each molecule. 4 molecules means 8 total bonds. If we can look up data corresponding to each of these groups of bonds, we're going to figure out which bonds are broken, which are these guys over here on the reactant side, and which bonds are formed over here on the product side. And the difference in the energies of these two sides, according to our equation, is going to get us the delta H for the whole process. So on this slide, we have again the reaction written as Lewis dot structure, showing us all the bonds present in both the reactants and product sides, as well as the enthalpy data, which is taken from our bond enthalpy table. Again, if you have not yet copied down that or downloaded and printed out that bond enthalpy data, I strongly encourage you to do that sooner rather than later so you have this information handy. So then, to calculate the total energy of the process, the delta H of the reaction, we need to take the total bond energy of our bonds broken, which are our reactants, and we need to subtract that or subtract from that, I should say, the total energy from our bonds formed, which is the product. So these again are our broken bonds over here, and these are our formed bonds over here. So we're going to use that equation from before, and we got to add all this up. Well, we said from before that we would have 8, so we'll start our calculation, 8 carbon to hydrogen bonds, which you recall from the table has an energy of 413 joules. We're going to add that to the 2 carbon to carbon bonds, which have an energy of 348 joules each. And these are these bonds right here. They're very easy to miss, and I think I forgot to talk about them on the last slide. And then finally, we'll add that to the oxygen-oxygen double bonds. We have 5 of those, and that gives us a total energy there of 495 joules, or kilojoules. This is our total bonds broken, and if you recall, these were the carbon to hydrogen here, these were the carbon to carbon here, and these were the oxygen to oxygen double bond here. From this information, we're going to subtract out the energy of bonds formed. That's going to be 6 times the carbon-oxygen double bond, which is 799 kilojoules, plus the 8 times the oxygen to hydrogen, which is 463 kilojoules. We put some closed brackets around here, and again, this is the carbon to oxygen bond formed, and this is the oxygen to hydrogen bonds that were formed. We should be able now to use our calculator to get some answers here. We can get the total energy from bonds broken, the total energy from bonds formed, find the difference of the two of those, and get our ultimate value for delta H. Using my calculator, I find the total energy from bonds broken to be 6,470 kilojoules. And I find my total energy from bonds formed to be 8,498 kilojoules. To finish this math problem up, we just need the difference of the two of these, which would give us a delta H of somewhere in the vicinity of 2,048 kilojoules for every 1 mole of propane that's burned. We can compare this number then to the measured value of delta H, which would be something in the vicinity of 2,044.2 kilojoules per mole. And we can see that our numbers are pretty darn close. These differences can be explained by some of the experimental error that's always present in the calorimetry process, plus the average information, the fact that we have to average data from our bond enthalpies, meaning if this reaction was done in slightly different conditions, those bond enthalpy values would have been a little different, resulting in a difference here of about 4 kilojoules of energy. Overall, I think it's pretty clear to see that using this methodology is not too taxing as long as you have the data and gets us answers that are pretty darn close to what the expected values are. Let's not leave this out, right? There should be a negative sign there. All right, so that's pretty much it for bond enthalpies. Problems do not get more challenging than this. They simply get longer as you get more and more complex molecules or more and more reactants and products. Let's change direction then and start talking about how to calculate delta H using a different method known as heats of formation. Just like before, we'll start with a definition of heats of formation and then move into how that formulates into a calculation we can use to calculate the delta H of a reaction. Our heats of formation is basically the energy gained or lost, this can be exo or endothermic in this process, in the synthesis of a chemical compound from its elements. So when you take the individual elements and fuse them together to make that compound, the energy it absorbs or releases in that process is known as the heat of formation, the heat it takes to form that chemical compound. This, by the way, can also be known as the standard enthalpy of change of formation, which is a more wordy way of saying it. I like to throw that out there just so you guys, if you see this information, you guys know what to recognize, and it means the same thing as heats of formation. It has a symbol, delta H sub F for heat of formation, and more commonly you'll see it with this little degree sign, or this little circle afterwards. What this little circle here means is that it's done at standard conditions, which we talked about standard conditions a little earlier in the year. The one that's really important here is the 25 degrees Celsius or 298 Kelvin. Turns out these heats are different at different temperatures, so to make this data shareable among scientists, we have a standard value at a standard temperature. Just to drive the point home of what a heat of formation is all about, we see a reaction down below. We're taking hydrogen gas, reacting it with oxygen gas, and as a result forming 1 mole of water. And we use that neat little trick that thermodynamic chemists like to use. We use the 1/2 here so that we guarantee we create 1 mole of product. And we see to make that 1 mole of product, the delta H for this entire process is negative 241.8 kilojoules. Well, in this particular scenario, because this is the formation of water from its individual elemental parts, that means the heat of formation, the standard heat of formation for water is negative 241.8 kilojoules. And this is how these values would be measured. You'd find a reaction that makes your compound from elements, and then you'd measure the delta H of that and use that as the heat of formation for that compound itself. So moving on then, the next thing to talk about is how is this data actually used to calculate the delta H of reaction? Well, heat of formation is really a measurement of the amount of heat energy stored in the entire chemical itself. You can think of it, with correct spelling hopefully, you can think of it as kind of the sum of all the individual bond enthalpies of all the bonds that are made in that particular compound. Now this is not how we get or heats of formation data. We talked about how we did that in the last slide, but it's a way of kind of thinking about how this works. So instead of having to do the calculation with bond enthalpies in 7 separate steps, heats of formation really take all that energy, bundle it up into one total number, and then we can use that total number in a very similar way to calculate the delta H of reaction. So in a chemical reaction then, you've got your reactants. This is where your compounds are broken down. Depending on the situation, that energy can be used or released. And then your products, again, these are where you're having your compounds formed, and again, you're having energy used and released. You can imagine then, just like before, the delta H of the entire process is basically the difference between the heats of formation from the reactants and the heats of formation from the products, the amount of energy you're gaining versus the amount of energy you're losing in each particular scenario. Just like before, this can be summarized in a mathematical expression that can allow us to calculate the delta H of a reaction. And just like before, our sigma here again means the idea of a sum. Basically what we're going to be doing is we're going to take all the heats of formation of the chemicals in the products and subtract that by all the heats of the chemical formations in the reactants. So again, just like before, we can look up this data, get sums on both sides, and subtract the two to get our delta H of the entire process. So to get that data, there's a couple things we need to know. First of all, if you're dealing with elements, the definition of heats of formation is the energy needed to make it from an element. I think it does not go as too big of a surprise then that the heat of formation of elements is always 0. You can't make elements from elements, they're already there. For compounds then, we do have heats of formation, and that's information that again will be available on a table. If you have not already done so, there should be a link to a table like this at the bottom of the page. Please get that table, please print it out and have it handy so that we have this data available to us for when we want to do problems later on in this video as well as later on in class. So this is where we get our heats of formation data. And then you take all of those products and reactants, all the chemicals there, add them up according to the equation above, find the difference, and you'll get your delta H value. Again, it's important to realize this is exactly the same as we did with bond enthalpies, except now we're doing it with data values for each chemical as opposed to data values for each bond. So this brings us to our last real problem of the day. The goal here again is to calculate the heat of the delta H, or the enthalpy of reaction, using the following information and heats of formation data that is provided for you. So we've got, in this case, methane reacting with oxygen gas to form carbon dioxide and water. And our real question in hand here is, what is the delta H of this entire process? Just like we talked about, you would go onto your table and you would look up the heats of formation data for all of these compounds, and you get data that looks a little bit something like this. You've got your methane, your oxygen, which is 0. That won't show up in your table, but it's an element, so by definition you should know it's 0. And then we got our carbon dioxide and water. And again, just from the formula before, it's going to be the products minus the reactants. So in this case, we're going to take the energy from the carbon dioxide, which is negative 393.5. And we're going to add that to the energy from 2 of the waters. There's 2 of them formed here, so you got to take the water data and multiply that by 2. Negative 241.8. So we're going to take the sum of all of that, and we're going to subtract it out by the sum of the reactants, because we said it was products minus reactants. Well, the CH4 has a delta H of negative 78.4. And that's going to be added to 2 times the 0 energy from water. Obviously, you can leave that term out if you want. And we can start doing some math here. Adding things up on the product side, I get negative 877.1 kilojoules. And that's going to be subtracted by the negative 78.4 kilojoules, which ends up being the total from the other side. Subtraction of a negative number means we add. And that adds up to a total for our delta H of this reaction as being negative 798.4 kilojoules for every mole of reaction. And just like before, we can take the answer we just got and compare it to known values of delta H for the combustion of propane, or methane, in this case, and we get a known value of 802, which we would measure with a calorimeter. And again, I think it's important to note that the 802 and the 798 are relatively similar to one another. Differences, again, can be explained by slight variations, uncertainty in some of these measurements, as well as uncertainty in the measurements in the calorimetry process itself. But again, the important thing is, remember, we're getting comparable values for these, justifying that this is indeed a reasonable way to calculate our values for delta H. Just to wrap things up, we can go over a list of things that you should now be able to do based on what we've talked about here. First of all, you should be able to define what bond enthalpy is and what heats of formation are, and be able to look all of that data up on a respective data table. You should be able to calculate the delta H of a reaction if you are given the reaction with Lewis dot structures and you are given bond enthalpy data. We talked about an equation and a process for calculating delta H from bond enthalpies. And likewise, you should be able to calculate the delta H from chemical reactions, just the chemicals this time, and heats of formation data. It's important to note that all of these things, plus Hess's law, all give you the same answer. You can almost think of all of these things as just being different tools to get at that information of the delta H of a reaction. And by the way, not even just Hess's law, but also this, right? Calorimetry gets you at the same exact answer, and that's measuring the delta H of a reaction. This again is just different tools for that in that toolbox to get to the same possible answer. In class, we'll spend a little bit more time reviewing some of these concepts, and we'll definitely give you guys an opportunity to practice some of the mathematics that goes along with this. I find the math is not difficult as long as you have a couple chances to explore it on your own.